All right, so let's get a head start on 4.3. In 4.3, we also have homogeneous differential equations, but in particular, we're looking at ones that have constant coefficients. All right, and so what we've seen in 4.2 is that what happens when we have non-constant coefficients. And what we're going to see in this section today and tomorrow is what happens when we have numbers as our constant or numbers as our coefficients. Okay. So an updated little flow chart here for us to kind of think about is we're starting with homogeneous second order differential equations. We've explored this idea that if we have non-constant coefficients, we can approach it with this idea. If we have one solution, then we can find the second solution. But one thing to note is we had to have that one solution. If we didn't have that one solution, we wouldn't have been able to do those problems. Okay, I'm sure you would feel really bad about that, but we needed that one solution to solve the step for the second. But what we're going to take a look at today and tomorrow is the cases where those coefficients are actually constants. In fact, they are numbers. And we're going to explore something called a characteristic or auxiliary equation. And tomorrow, we're going to be looking at 3 different cases for those solutions. Okay. It will be important to know these 3 if you plan to take another differential equation course, like ordinary differential equations or partial differential equations, you will see these 3 cases again. Okay, so they are definitely something that come up again. So this is sort of like more of like a flow chart of where we're at in our chapter. Remember, there's a whole separate branch that talks about non-homogeneous second order differential equations, but we'll get to those next week. Okay. But what we're going to talk about right now is this idea of finding solutions. Okay. And so I think some of this seems magical when people are like, well, let's assume this, let's assume that. And I want us to kind of step into that role a little bit and just think about all that we know about calculus and think about what might a possible solution for y double prime minus 9y equals 0 be. Okay. I think this is a very open-ended question, and it can be really hard to think about where to start. So what I want us to do is start with this equation. We're going to do something we haven't done yet. I'm just going to go ahead and add 9y to the other side. Okay. Now, if I read this equation and sort of interpret what it means, this is really saying what function has a second derivative that is equal to 9 times the function. Right? Y double prime equals 9y means that you have some function y. And when you take 9 times that function, you actually end up with the second derivative. Right? So using that, what are some ideas we might have? What might make a good choice for y? will give you a hint. Sometimes a little chain rule is helpful here. All right, well, maybe let's back up a step. Can you tell me a function where its derivative is actually equal to the function? Yeah, e to the x, right? E to the x, no matter how we feel about the number e to the x is so special because its derivative is actually itself. And its second derivative is actually itself. So how might we modify that so that we actually have a function where the second derivative is 9 times that function? What can we build from? Right, because if I have this, I end up with y prime equals e to the x, y double prime equals e to the x. That means that they're all the same, but how do I make it 9 times? What can I modify here?
If it was e to the 3x.
Yeah, let's try that. E to the 3x. I take that first derivative. I better use my chain rule. I take the second derivative. I better use that chain rule again. Exactly. So I bet that one of the solutions for this differential equation is e to the 3x. Because it makes this differential equation true. What else might be a solution? Where at the end, the second derivative is 9 times the original function.
Is it something with sine and cosine?
Sorry, say that again.
Would it be something with sine and cosine?
I think we can actually, it might be, but I think we can modify something that we have here. Right, because with sine and cosine, I think that second derivative will get you to the opposite sign. Like if I have sine x and then I take that first derivative, I get cosine x. But when I take that second derivative, I get negative sine x. So almost, but we have that wonky sign that is there. What about this? Do you think that could be a solution? I know I'm asking us to think at the end of class after I just vomited all these procedures all over you. But let's take that first derivative and see. -3 times -3. Oh, shoot. Gives you 9. 9 times your original function. Any other ideas? Let's see if we can come up with one more. Don't all jump at once.
But would just 9 e to the x work?
Let's see, 9e to the x. I take my derivative and I take my second derivative. I have that 9 here, but we have something that is still the same as what we started. I think that's a good guess. But what I like about what you said is, what if we just put a number in the front? Like, my favorite number is 5. What if I had 5 e to the 3x? Would that still give me a second derivative that is 9 times my original? Right? And it turns out that, let's see, these ones with the red x do not satisfy this differential equation, but these ones with the green smiley face do. And so it might be natural for us to think that in general, maybe we expect that we get solutions of the form some constant e to the plus or minus 3x, right? All the ones with the green smiley face have some sort of number in the front. Sometimes it's 1, but there's something there. And then e to the positive 3x or e to the negative 3x, all right? Now, don't worry, this section is not about you guessing solutions like this, but I think it's a useful exercise to think, what might these be, right? It is all equations, but what does that equation actually ask? This is what it's actually asking us for, okay? Now, the last thing I want to say before I leave you for today is we're going to revisit this principle of superposition. Okay, so I said it earlier. I did not write it down, but I said it earlier. And so here's what the principle of superposition says. If we have one solution, y1 of x, and we have a second solution, y2 of x. Okay, so if y1 of x and y2 of x are two solutions to a linear homogeneous equation, then so is the following, all right? Meaning we can write the general solution as y of x equals c1 y1 of x plus c2 y2 of x. Right? In other words, this is a linear combination of solutions. So linear combination of solutions will give you the general solution. All right, so this principle of superposition says that if we have these sort of pieces of the solution, in order to get the whole solution, we can write the pieces as a linear combination, and then we will arrive at the general solution. Okay. And so I think that's where we're going to stop our conversation for today. What we're going to do tomorrow, we're going to come back and we're going to see if we can generalize what we talked about here. All right, it will not be a long conversation, but I do want to come back and generalize this. Then well, then we are going to take a look at 3 cases. So you got case 1 here. You got case 2 over here. And you have case 3 over here. All right. Figuring out the different cases will be really useful for your homework. So we're going to think about like not only what are the cases, but how do we know what they are and what does their solution look like? All right. So that's where we're going to pick up tomorrow. So I will stop the recording here.